Bismillah ar-Rahman ar-Rahim. This is a steel structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 19, 2020. In the last few classes, we did check if the flexure elements, which is beams, are safe under loading conditions. And today, inshallah, we will check if they are surfaceable. And let's know what does it mean to say surfaceable structure. Surfaceable structures is that the one performs satisfactorily, not causing any discomfort of unsafety for the occupant or users of the structure. معنى الكلام إنه surfaceability إنه الستراكشر يكون ما في أي دلائل إنه هذا الستراكشر يعني unsafe مش آمن للشاغلين occupants أو users مستخدمين هذا المنشأ. And usually being surfaceable means that the deformations, which is mainly the vertical deformations or deflections, must be limited. So we have limits for these deformations. Any structure or structural elements, it has a deflection. But we should limit this deflection. يعني أي منشأ أو عنصر إنشائي راح يكون فيه deflection له. But we need to, let's say, outline the acceptable deformation limits. يعني لازم نحدد قيم محددة فيها إذا تجاوزها أو تجاوزت deformation, we should say that this structure is unsurfaceable and we need to do to do an action. Yeah. Sometimes excessive deflection means if we have extra deflection, usually indicate a very flexible beam. So a beam is very flexible, so we do have, let's say, excessive deflection. And this will be a problem because this beam will be connected to a column, and this column might be damaged by a small deformation. يعني ممكن هذا البيم مرتبط أو هو it's connected to a different, let's say, structural elements. منهم طبعا راح يكون column. فبحالة إنه يصير البيم عنده أي deformation ممكن يأثر على الكولوم which might lead to collapse. يعني ممكن يصير لنا انهيار. Okay. And sometimes users or occupants of the structure may view large deflections negatively and wrongly assume the structure is unsafe. يعني مستخدمين المنشأة. Okay. ممكن يتطلع if you see there is a big deflection يعني عندك deflection كبير ممكن هذا يعطيهم شعور بعدم الأمان يعني the function or let's say the structure will lose its functionality. يعني بمعنى الكلام يا شباب احنا لازم نشيك البيم على المومنت سترينث والشير وبعد هيك these يعني خلينا نسميهم strength limit states هذول بيتعلقوا بالمقاومة وبعد هيك لازم يكون عندنا يعني we have to do check على الديفليكشن اللي هو هون بنسميه surfaceability limit state. Okay. Let's say here for simply supported beam as the common beam here. Let me do here a simply supported beam. Loaded with the uniform distributed load here. And the load intensity is W. Okay. So the deflection or deflected shape is going to be like this. And the maximum will be at the middle here. So how much the maximum deflection here for this case is equal 5 WL to power 4 dividing by 384 EI. So this is the maximum deflection which happens here at the mid. Okay. And we can get this by different ways. And I think all of you passed the structural analysis 2 class, or let's say here structure 1, you will be able to find the deflection by different methods. Table 323 shear moments and deflections in the steel manual gives you different cases with, let's say, the formula here for the reaction. If you see, let's say this is a simply supported beam loaded with the uniform load, so tells you simple beam uniformly distributed load. So the total equivalent load all the time, it's W times the L. This is the reaction, this is the shear maximum moment, and it tells you at the center, so which is here, this is the maximum moment. And this is the general equation for the moment. You can get the moment anywhere. Okay, this is the maximum deflection. So here is the maximum deflection, and it tells you at the center. Okay, so as I mentioned to you, and this is equal 5WL to power 4 dividing by 384 EI. Okay, and this is the general equation for the deflection. So if you want to find the deflection anywhere, not at the center, you will be able to use this equation. And there are different cases here. So this is simply supported beam. Case number 2, load with increasing uniformly to one end here, which is this one. It's a triangle here, loading condition. And here is the maximum deflection, and here is the general equation for the deflection, so you can get the deflection anywhere, and so on for different cases here. It's a long one here, so you can have this with you in the exam to help you to find the deflection if you need to do such thing. Okay, so let's get back to our textbook. So the table 323 in the steel manual will help you to get the deflections, shear, and moments. But for some, let's say, unusual situations, standard analytical methods can be used. Let's say method of virtual work, moment area method, conjugate beam. ممكن عندك طرق كثيرة تستخدمها حتى توجد الدeflection. Okay. So as I mentioned to you guys, deflection is a serviceability limit state. يعني هي مش strength limit state. Strength limit state اللي هو بتعلق ايش؟ هون مثلا بالبيم اللي هو shear و bending moment capacity. But deflection is a serviceability limit load. So we should compute the deflection under serviceable loads. يعني loads لازم يكونوا factored. So they should be unfactored load, serviceable load. يعني they, as they are. So all the time, as I mentioned to you, we do have, let's say, limits for the vertical deflection. So if you look at table 5.4, deflection limits, so this gives you type of members. This is the maximum live deflection, or load deflection, dead load plus live load, snow and wind load. So here is the type of the, let's say, member, roof beam. So if we do have, just a minute here, guys. Let's say supporting plaster ceiling, the maximum live load deflection should be L over 360. And we do have different cases. We will solve an example right now and show you how we're gonna use the limit or deflection limits. So let's move down to example 5.9 here, page 226. In this example, the problem statement says compute the dead load and live load deflections for the beam shown in the figure 5.23, which is this one. Simply supported beam loaded with a uniform distributed load. Here is the dead load, and here is the live load. Dead load is 500 pound per foot, and live load is 550 pound per foot. And the length of this beam is 30 feet, and this is the cross section of the beam, which is wide flange 18 by 35. So, and here gives you the maximum permissible live load deflection, which is L over 360. Is the beam satisfactory, and is the beam adequate for, let's say, serviceability limit state, which is the deflection? So let's check and see if this beam is okay or not for the deflection. And this beam is supposed to be checked or designed, let's say, for bending strength and shear. And the last step should be the deflection. Okay, if you're just, I just mentioned to you that the maximum deflection for the simply supported beam loaded with that uniform distributed load is this much, which is 5, let's say here, it's 5 WL to power 4 dividing by 384 EI. So right now we have dead load, we have live load. So we will check that for dead load and then for live load. But here in this example, just we have the limit for, let's say, live load. Okay. So if you look here, for the dead load here, guys, here, it's 5 times, let's say here, the distributed dead load, which is converted here, guys. If you look at this one, is right now, it's 0.5 kib per foot. And then we will convert it to inch here, okay? So it's like this 0.5 kib per foot. And to convert it to inch, why we need to convert it to inch? Because the limit is 3 or L over 360, and this should be in inch. So it's good to get the limit or the deflection in inch instead of feet. So this one here, it's 1 foot here, it's equal 12 inch. So that's what we did here, okay? Times L to power 4. L is 30 feet, and this is just 4 feet. To convert it to inch, times 12 to power 4, dividing by this much here, times the Young's modulus, times the moment of inertia here. This value, it's you can get it from the manual, table 1.1 for this cross section, which is 18 by 35. So this is IX, okay? And I think you are mature enough and smart to get it. So here, this is the deflection due to the dead load. يعني هاي deflection بسبب الdead load. If we're gonna do that for the live load, same here, same formula, since we are dealing with the same beam and cross section. So it's gonna be 5 times, and this is the live load, but in kib per foot here, okay, times or dividing by 12. This is the length in inch to power 4, dividing by this, and this is I. So here is the deflection due to live load. High deflection بسبب live load. So the maximum permissible live load deflection, which is طبعا احنا راح نقارن بس هاي لأنه فعليا we don't have a limit for this one in this example, but for we can get it. So here it's L dividing, this is the limit was giving to us, L dividing by 360, which is 30 length, times 12 to convert it to inch. دائما لازم نحولها لإنش, dividing by 360. So this one is equal 1 inch, and this one is greater than the value we got here. So the column is, or the beam, sorry, is okay for deflection or serviceability limit state. The beam is okay for this limit state. Okay, so you should be able to check the deflection for any type of beams using table, let's say 323 in the steel manual, the one I just showed you, or for any type of loading, you should be able to do that. So let's move right now to the design of the flexure elements. Let's move down. So to design a flexure member, we need to select a cross-sectional shape that have enough strength and will meet the serviceability requirements. Once we have enough strength, that means we are safe in terms of strength limit state, which is flexure and shear, okay, strength or capacity. So as I mentioned earlier too, guys, all the time in the flexural beam elements, flexure is the primary or the critical, let's say, term here or thing, than the shear and let's say the deflection. So all the time we should design the beam or flexure beam for, let's say, flexure strength or capacity, and then check for shear or, and deflection later. يعني الكلام يا شباب انه اذا بصمم بيم لازم اول شيء اصممه بناء على الفلكشر سترينث اللي هو البندنج مومنت، اوكي؟ بعد هيك اشيكه على الشير زي ما عملنا المره الماضيه، وبعد هيك ان شاء الله بنشيكوا على الديفليكشن. So to design, or let's say the steps to design a flexure element, let's see these points here. The first step is to compute the required moment strength. Means we have a loaded beam, so for the LRFD method, mu here, which is the maximum moment, need to be checked, and for ASD method it's m sub a for, let's say, surface load. And easily guys, if we do have a simply supported beam again, and here is the loads, let's say this is W, we need to compute the required moment strength. Means what is the maximum value for the moment here. So the maximum for this case, it's WL square over 8. And this is just a general case, but you have to be able to find the moment or the maximum moment for any type of beam. And if you do have a beam like this, let's say here and here, this is overhang beam loaded in this part. So you should be able to find the maximum moment. It's a basic statics. يعني تقدر توجد maximum moment. طبعا in this case for LRFD method, this one should be factored load اللي هو يعني 7 cases. For ASD method should be unfactored load, which is the surface load. So I think that's okay for you. And all the time guys, the beam itself, it has what we call it self weight. It has a dead load. يعني هذا البيم له وزن. الوزن هون is going to be nothing compared to the total dead load. Okay. فايذر يعني هون at the beginning احنا مش عارفين شو السكشن اصلا حتى نعرف شو الديد لود له، ماشي؟ سوري السيلف ويت له، ف we can ignore it، انه نلغيه في البدايه نعتبره زيرو وبعدين ونكمل او نفرض قيمه يعني ونحل بناء هذا الكلام. But all the time when you do assume something, you have to verify your assumption later. يعني إذا عملت assumption هون بعد ما تختار السكشن لازم تعمل verification، يعني تأكيد إنه فعليا اختيارك it's okay or not. So all the time let's neglect the self weight of the beam. We'll continue as it's zero. Once we select the beam cross section, we will include that and recalculate the moment to see if we are still safe or not. وطبعا usually it's not a big deal، راح نكون إن شاء الله تمام حتى بعد ما نضمن اللي هو self weight. Okay, so this is step number 1, which is here. You can read it guys in details. So here, okay, and step number 2, we need to select the shape that satisfies the strength limit state or requirements. Means guys here we need to let's say assume a shape وcompute the available strength، يعني نوجد قديش moment available moment فيه قديش بيقدر يحمل، وبنعمل comparison with the required strength اللي احنا فعليا بنحسبها في الخطوة number 1. So and this is gonna be you might need to do that several times. It's a trial and error let's say method. And after that we have 2 ways to do that here guys, either to do it manually by the formulas, and we might use the beam design charts in part number 3 in the manual, and we will show you how to do that in example 5.10. Okay, so step number 1 to calculate the maximum moments. Number two to calculate the available moment، يعني قديش هذا الكروس سكشن بعد ما نكون اخترنا كروس سكشن قديش ممكن يحمل، وبنقارن بستيب نمبر 1. ستيم طبعا هون ستيم نمبر 2 في عندنا 2 ways to do it، انه نستخدم مانيوالي او نستخدمه من التيبل part 3 from the steel manual. ستيب نمبر 3 check for shear. اوكي بنشيك الشير زي ما عملنا المره الماضيه، وعندنا تيبلز اللي هم ممكن يساعدونا، وبعد هيك بنشيك for or check for deflection. فيعني البروسيجر واضح جدا يا شباب. اوكي نحسب الماكسيمم بنقارنه بالافيلبل سترينث او مومنت سترينث بعد ما نكون اخترنا السكشن. 2 ways to do that. بعدين بنشيك الشير، بعدين بنشيك الديفليكشن، وهذا ال usual practice for the design of the flexure beam. So let's solve example 5.10 here. on page 227. So the property statement says, select a standard hot rolled shape of A992 steel for the beam shown in the figure 5.24. So this beam, we need to check or to select a cross-sectional. It's a hot rolled shape. Okay. The beam has a continuous lateral support and must support a uniform surface load of 4 kips per foot at the live load, and the maximum permissible live load deflection is L over 240. يعني هو ده الليميت للماكسيمم لود، وهذا البيم بس بحمل هون عندنا لايف لود. Okay, the first step we need to ignore the self weight of the beam. يعني نعتبره انه zero. And if you look here, and we're going to start with LRFT method. So the load intensity is 1.2 dead load times or plus 1.6 live load. Dead load is equal 0. ليش equal 0? We don't have a dead load here, and we assume the self weight of the beam equal 0 in the beginning, initially. Okay, just initially here. And once we select a cross section, we will get back and verify our, let's say, assumption here. So this one will be 1.6 times 4.5 kip per foot here, and this one here is 7.2 kips per foot. And you know here the maximum moment for simply supported beam is W L square over 8. And guys, this is not the only case we will deal with. So we might have different cases. يعني مش بس هاي الكيس الوحيد ممكن نتعامل معها. Okay. So here it's W, and W it's here, guys. We got it from here. It's 7.2 times L here. L is 30 feet, and we did not convert it because we got the load here. It's per foot. يعني مش داعي نحولها. Dividing by 8. So this is the required flexure strength. يعني بدنا cross section which is 810 kip per foot. كيب فوت حتى بدنا كروس سكشن يحمل هذا على الأقل هذا اللود أو أكبر منه. Okay. So let's move down here. And we need to assume first if the shape is compact or non-compact. Let's assume it is compact shape. Okay, so it's compact shape. And you know, guys, as mentioned in the problem statement, it has a full lateral support. ولما حكينا إنه full lateral support بتتذكروا إنه in this case full lateral support is like this. So Mn is equal M plastic. So M plastic is equal, let's say, yield stress times plastic section modulus. So here, guys, so the available capacity should be, this is for beams here, sub beam, it should be greater than or equal the applied moment. يعني هاي لازم تكون أكبر من الapplied moment اللي أوجدناه هون. طبعا this one here, as I just mentioned, اللي هي is equal Fy Zx, and this should be greater than or equal اللي هو 810 kips foot. So right now, this one, it's okay, it's known for us. This one is known for us since we are dealing with 992 steel. And this one is unknown, and this one known. So Zx here is supposed to be greater than or equal the applied maximum moment dividing by, which is phi b here, yield stress, and this one here is equal 810, which we did calculate here, dividing by 0.9 here, phi, and times 50, and this one should equal 216 inch to power 3. So this is Zx. Right now, we need to go and pick a cross section with Zx is greater than or equal 216 inch to inch cube. Okay. If you remember, we did use this table to find here L P L R, and sometimes to find ZX. And this table, guys, for wide flange shapes, and which will be selected based on ZX زي ما بنعمل الآن. طبعا there are other tables for different cross sectional shapes. ممكن يكون for C channel, for S shape, and there are many, but here we are just dealing with wide flange, and I should get you the other tables. Okay, so here this is ZX, and our ZX or required ZX was equal 216 inch cube. So that's what we need, something greater than or equal this much. If you see here, let's go here. So we can go with this one here, we can go with this one here, and let's go with this one here as it's selected in the textbook. So it's wide flange 24 by 84, and ZX is equal here to 124, and these values we will use them later here, guys. And here is for the shear, and we will see how to do that later. But here, guys, W or wide flange 24 is the depth, okay? 84 is the weight. So this is the self weight of the beam اللي هو هون بعد once I got selected or select the beam اللي هو 84 هون pound per foot, okay? So let's get back to our example and see how we're gonna continue with this one here. Okay, guys, here we did select this shape, which is wide flange 24 by 84. And right now, since we know the cross section, the distributed load is different, okay? So for LRFD method, it's gonna be 1.2 times the dead load. And here's the dead load, just the self weight of the beam. So the self weight of the beam, it's 84 pound per foot. And dividing by 1,000, it's going to be 0.084. Here it's kip per foot. Okay, so 1.2, and the dead load is just the self weight of the beam اللي هو وزن البيم. وهون nothing will change, نفس الشيء. So the factored load is 7.3. 0.1 kip per foot. It's a little bit greater than what we had. اللي قبل كان 7.2. Okay, so right now we need to check. So the maximum, and then كمان نشيك مرة ثانية the maximum moment. So the maximum moment is the same formula here, WL square over 8, but W is different here, so we need something to carry this much or more. قبل كان إنك كم هذا كان based on this one here, it's 810 kips foot, so this one should be here. So let's check the required, or here the elastic section modulus. If you remember, this should be greater than or equal mu, and mu here is the new value, which is this one times 12 here to convert it to inch, dividing by phi here 0.9, then this should be or is equal to 219 inch cube, and this one is still less than the ZX for the selected cross-sectional shape اللي هو wide flange 24 by 84. So right now let's see how much this section will carry. This section right now, we know that Dx for this section is greater than the required one, and this is the required moment. So how much this will carry? So let's use the table 3.2 for wide flange here, if we deal wide flange, and see how much phi b this for LRFD method. So how much this value, and this value here, which we'll get here, is supposed to be greater than this value. It should be equal or greater than this value. So let's go to the table 3.2 and see how much this value. So this is our selected cross-sectional shape, wide flange 24 by 84. So this is the ZX, which is greater than 219, which is the required one. And here for LRFD method, guys, keep foot here, the capacity for this one, or the design flexor strength for this cross section, is 814. okay, for Al-Rafdi method. And if you remember, the required one was يعني اللي هو mu was 821 something, which is 0.4 اللي هي kip foot. So right now PMN 840 kip per foot, which is this value here, that one we got it here, greater than this, so greater than this, so we are safe in this case. So this section is or works perfectly for our loading conditions here. And if we do that, guys, same here, if we do that for ASD method, and ASD method here, we will use the same maximum formula for mu, but here mu is going to be y w l square over 8, but this is going to be surface load. Okay, if you do that, you will get Zx, and if you check, and you will see that it's going to be something less than this, the required one, so this is going to work. Okay, so by this we did check this beam or selected beam for the flexure strength. Okay, so right now we need to check that for shear. So this one here, the shear for this cross section is 340 طبعا هون kip, because shear is capacity. طبعا this is for Al-Rafdi method. Here for ASD method we can do the same thing. So please memorize this number, which is 340 kip, and let's get back to our example and see how we can get the maximum shear, which is the maximum applied shear, اللي هو كم عندنا shear لازم نقاومه بهذا الكروس section. Okay. For simply supported beam, once again, which is our case here, and we might have different cases, and this is L, the maximum shear will be at the supports here, which is WL square, WL over 2. This is the maximum shear. And same here, which is the reaction. So how much this one for Al-Rafdi method? This is the factor load for Al-Rafdi method, and this includes the self weight of the selected beam. يشمل الويت selected beam. So this is L in feet here, or in foot, dividing by 2. So this is 110 kips. From the table, we got the, let's say, the shear strength 340. So 340 is almost 3 times greater than the required one. So this one is okay for the shear. So as I mentioned to you all the time, shear is not a big deal in the beam, but it might be sometimes, but in the general practice is not. Okay, right now this is step number 3. Step number 1, select or calculate اللي هو mu. Select number 2 اللي هو get a cross section و calculate the capacity. طبعا two ways إنه كيف نحسبه. Step number 3 to check the shear, which is this one. Step number 4 to check the deflection. Okay, and it told us how much the limit for the deflection. So this one here, L over, this is the limit, L over 240. So the limit is 1.5 inch. So, and here we did convert to inch because that's what should be all the time. Okay, so our maximum deflection should be less than this much under this loading. يعني احنا for simply supported beam, as mentioned to you, it's equal this much, which is 5 W on hon for live load. Okay, because it gives us just for live load. اشيك بس اللايف لود. Okay, انه هو اعطاني انه maximum limit for live load. So it's gonna be 5 live load, which is 4.5. طبعا هم بحولها ل inch. This is 30 inch to power 4 dividing by 384 times EI here, and I you can get it from the manual. Okay, and the value is 1.19 inch, and it's less than the limit here, so this beam is okay. So this beam, the cross section we just selected, it's okay for the strength limit states اللي هم moment to shear, and it's okay for the self serviceability limit state وهيك بكون we did design a beam with these steps. طبعا يا شباب بس الستبس هاي 4 steps يعني follow these steps and you will be safe with your selection. Please, if you do have any questions, send me an email or chat with me on Microsoft Teams. ويعطيكم الألف عافية.